Okay, so my name is Jan Granlund. I work as an industry process consultant expert at SIMULIA Euronorth. And the topic here is really realistic simulation made easy. And the basic underlying idea here is that if we were to have a robust nonlinear simulation tool, we would be able to stop making assumptions and perform realistic simulations. Such a robust simulation tool would be requirements of that would be to have extensive contact mechanic capability, to be able to deal with large deformations and advanced material models. If we were to have a single tool model that would also be able to incorporate all kinds of physics that our products will experience in the actual working environment. That will also help us to actually make better products. And that's kind of the underlying idea about the activity at Dassault Systems. And the vision, the target of our activities at Dassault Systems is to make realistic simulation an integral business practice in order to explore and discover and understand product life and nature. And the aim with that is, of course, to reduce the need for costly physical testings, and for that purpose to allow us to save time and money, of course, and more importantly also combining that with an improved quality. What we see on the screen playing right now are a couple of examples from our customers. On the left-hand side, from Mechanical Design and Analysis Corporation in Japan, we see a comparison between a test and simulation of the crushing of an empty soda can or aluminum bottle. On the right-hand side, we see a crash dummy or side impact crash analysis. And both of these are, of course, as we can realize, tests and experiments which can be fairly expensive and cumbersome to perform. So SIMULIA, which I represent, is actually not a product or a company, but it's a brand of Dassault Systems. And this brand is populated by products, which in this context are mostly Abaqus-based analysis products. We also have process management and optimization tools for managing parametric optimization. We have non-parametric optimization tools called Tosca for shape and topology optimization, and also for the sake of completeness of product development, we also have FE-Safe for assessing durability aspect of product performance. It's actually more to it than that, but that's what we're going to talk about today. Dassault Systems is a fairly big company. I'm sure these numbers are not necessarily updated, but we're more than 20,000 passionate people around the world. And we're really a long-term driven company, which means that we have some majority shareholders that controls the company, and we can as such undertake very long term development projects. We have more than 290,000 customers around the world using our products. So from now on, I'm going to focus more on the simulation or analysis products on the SIMULIA brand, and I'm going to start with Abaqus. So Abaqus is kind of a bit of the core of the mechanical part of the SIMULIA platform, and Abaqus is a finite element, a general purpose finite element software. It consists of two solvers, Abaqus Standard and Abaqus Explicit. It's designed for production use, even though it's a very advanced piece of software. But part of the design criteria initially was that it was supposed to be a tool for production use, which means that we have very severe quality procedures and so forth to ensure that the results are measuring up to high quality standards. The solver product is accompanied by an interactive product called Abaqus CAE. Complete Abaqus Environment is actually stands for, which is the graphical user interface where the user can do a pre and post processing of the simulation models. The target or the goal of our offering is really to provide a simulation tool covering the full range of needs for simulation. So what we see on screen here on the classical view on the bottom left hand side, we would sort of envision oftentimes designers or less qualified simulations being done, and a classical expert would be on the upper right hand side. Oftentimes the expert performing very advanced types of simulations. Of course, both of these conditions are typically coexisting in current organizations, and the goal from our side is to provide, through various customization capabilities and so forth, possibility to actually almost completely offer solutions in all parts of this diagram. So by customization, we can deploy very advanced simulation workflows, presumably developed by the experts, but they can be captured in customizations and sort of consumed by maybe less experienced users. We have a very good footprint across almost any industry today, which again is an evidence of the generality and the quality and the sophistication of the code. So we have a very comprehensive library of material models and capabilities that lends itself very good to almost any industry. I won't read it out all of them for you, but you can imagine that it will work for, or I would say, any industry that we know of today. So a little bit more specific then about our products. So Abaqus CAE then is the graphical user interface the users will interact with. It's a modular and well organized and easy to learn user interface. It uses an object-oriented paradigm, navigation through a model tree. It's all fully customizable. It's, I would say, relatively new. The first version was released in 1999. So this type of software, it takes a while to become really mature. But in terms of analysis pre-processing, it's I would say really a very mature and capable tool that I think most of our users finding to be a good partner in the simulation workflows. Although it has a moderately competent geometry modeler in it, we oftentimes rely on powerful CAD interfaces to allow company-wide CAD geometries to be imported and potentially repaired or modified to meet the specific requirement for setting up simulations, which could be, of course, adding pieces of geometry, but it also could be simplifying, reducing undesired aspects of the geometry, which doesn't really contribute to the value of the simulation. Structure simulations, as we see it here, oftentimes involves, or most of the times involves, meshing. So meshing capabilities are critical. And for TET meshing on 3D, there is a fully automated remeshing algorithm that will mesh any geometry. We have a semi-automatic hex meshing capability that will require some amount of user intervention to split the geometry into simpler topological cells to be able to produce hexahedral element shapes, which generally are more efficient than tetrahedral elements, but on the other hand, it takes a longer time to generate the mesh. Abaqus EA also contains a powerful tool for visualization of the results, which of course is an important aspect of doing simulations. So it's capable of managing large models, provide for transparency, plots, view cuts, probing, animations, synchronized viewports, XY plots, and so forth. So it's a very, I would say, attractive way of actually presenting the results we produce with our simulations. It's also, as I mentioned, customizable, and we use Python as a third-party scripting tool for enhancing or capturing workflows. So the simplest way is really to use a macro mechanism. So repetitive tasks can easily be recorded with the macros, which are Python journal commands from the process we are capturing, which can be edited and enhanced, of course. We can further build new functionality, add functionality on top of existing general purpose applications. We offer, there is also an API for creating additional graphical user interfaces. The simplest one is really just an interactive drag and drop GUI builder. We call it really simple GUI. So the user can by drag and drop operations create new dialog boxes, which can be used to provide the user a nice interface for adding data. So as an example, we see on the left-hand side here the out-of-the-box view of Abaqus EA. On the right-hand side, we see the Abaqus knee simulator, which is a customization where, as you can see, there is a knee joint for presumably an implant of some kind, where all the other aspects have been hidden, and the user of this application will only see the aspects pertinent to the current model, can edit data properties and submit simulation and immediately go to view the results. So our analysis products, a little bit more in detail. We rely on robust solver technology. We constantly update the solver technology also to be effectively used in the current hardware. So there's a constant ongoing work for adjusting application file databases and so forth to be working efficiently with the current hardware environment. The first version of the solver code were in 1978, and early 2000 we made the previous big change in code structure for allowing for more native Windows applications and so forth. This is one example of maybe one of the more prestigious customers, BMW, which since the last plus 15 years has come a very long way in towards the goal to eliminate prototype hardware testing. So they assign very high quality to the predictive simulations in order to avoid having to do very expensive prototype testing. So as far as I know, hardware testing in terms of crash analysis doesn't really occur until the pre-production series are available. Central to powerful simulation tool is the availability of material models that are being used in the engineering community. And we have an extremely extensive library of material models, including rubbers, metals, composites, linear, non-linear material, isotropic or anisotropic with dependence of loading rates and temperature dependencies and so forth. We also have comprehensive offerings for modeling of soils and rocks and concrete and ceramics and pastes and polymers and so forth. So and also strong capability within the field of damage and failure modeling. I will come back to that a little bit later on in my presentation. Importantly, though, that these are material models, we do not necessarily provide sort of calibrated data for it. So that could occasionally be a challenge, of course, if you want to do really advanced types of simulations. I mentioned previously that we have two solver products. Abaqus Standard is not kind of a lightweight or a simpler tool in any way. It's actually the most comprehensive solver that we have. It's based on an implicit solution technique, which doesn't necessarily mean a lot for some of you, but it means that we can solve for pure static events as well as dynamic events. Simulations can be linear or non-linear to the degree decided by the users, so depending on how much non-linear features we include in our model, it will be gradually become more and more complex. We see some examples playing on the screen here, from classical stress analysis, of course, to mounting analysis, sealing analysis, noise. So this involves activating also acoustic fields and so forth. Abaqus Explicit is complementing that. It's based on an explicit time integration. This solver technology was initially intended for high-speed transient dynamic events like drop tests or crash tests. But it has also proved to be quite efficient for very highly nonlinear quasi-static events such as rolling or forming simulations. So this is why we see some of those applications playing on the screen. But very rapid events like impacts, explosion analysis, and so forth are probably home territory for most of the category of explicit analysis. Both our solvers have extremely robust and accurate contact capabilities. So contact capabilities are required whenever there are more than one part which interact with each other. From the human eye, it kind of looks trivial, but from a numerical standpoint, this is a very complex aspect of simulations. Both our solvers are currently using predominantly what we call a general contact capability, so the user can just ask for creating contact properties for all the exterior surfaces of geometry. And that's only a couple of mouse clicks away. Then simulations can, of course, be gradually more refined by adding more complexity to the contact aspect of the simulations. Even though in a general sort of a context, a lot of simulations are not necessarily very advanced, but the trademark of Abaqus simulations are the capability to be able to do what I call advanced analysis here. So advanced analysis could be, for example, ones which contains multiple steps. So what we see here is a turbine or an impeller or something which rotates with relatively high speed. So just the fact that the turbine here rotates at several thousands RPMs will introduce some centrifugal stresses which will change the stiffness of our structure. So if we were to do an eigenfrequency analysis of this product, we would in reality have to take into account at what operating RPM this eigen frequency spectra is calculated. So this is an example of multi-step advanced type of analysis. This could also be cases when we take into account assembly types of analysis. So whenever things are assembled with bolts and nuts, for example, we usually tighten these things before we subject our product to the service load that we would be interested in simulating. So it's really important for having accurate final results that we capture the history of events pertinent to the product life. Another example of advanced analysis are to be able to include damage and fracture. We see here a couple of examples of that. On the top right-hand side, we see cracks being initiated, and we see a crack propagating. So we see also a picture from a test, and the simulation very accurately captures this behavior, and this is what most people are maybe automatically kind of assuming that we mean when we talk about damage and fracture, that things break, and we want to try to design us away from these failures to occur. The other animations that we are playing here are examples where we actually are using the damage for providing the product performance. Both of these are effectively energy absorbing structures. The bottom left hand side here is actually the part of I think the structure of the seat of a helicopter. So in the event of a crash of the helicopter, we want to protect the passengers and the pilots from too severe impact. So there is a composite structure that is designed to break, but also at the same time dissipate energy to mitigate the impact effects of the passenger on the seat, which we don't show on the picture here. Packaging industry as well is an example where simulation of the opening mechanisms of consumer packages are actually where damage and failure are part of the product performance, because we want the package to open nice and smooth when we try to open it, but we want to avoid the package coming open when we drop the juice package, for example, and so forth. Other advanced types of analysis are the capability to simplify away some of the contact analysis by introducing connector elements. So for system level analysis, it might become unnecessarily expensive to do full contact analysis in between each and every part of such analysis. So we can save some simulation time by abstracting away some of these contact aspects by two-point idealizations. Multiphysics analysis are also, of course, part of advanced types of analysis. So what we see here are multiphysics in the sense that we involve more than one physical field. So thermal mechanical, for example, it could be structural acoustics, it could be thermal electric. There are multiple variants of multi-physics simulations available on the SIMULIA platform. Fluid structure interaction is also an example of multi-physics types of simulation. This is where there is fluid, could be a gas or water, as we can see on the top right hand side, interacting with the structure, and we need both fields to accurately compute and simulate the product behavior in its real environment. There are multiple ways of doing this type of multi-physics simulations. In particular, I want to highlight for you some of these things which we call native multi-physics simulations. So these are all examples of simulations done entirely inside Abaqus, not necessarily having to involve an external fluid solver or so. So for these purposes, we have Eulerian formulations, or we have particle methods. They both kind of offer similar type of capabilities, but they have pros on different fields of applications. Another field which we have invested a lot of development the last few years on has been to provide simulation technology for additive manufacturing processes. This is a kind of a relatively new manufacturing technology which attracts a lot of interest in many fields of the industry. In terms of simulation, or structural simulation, or thermal simulation, there are some significant challenges here. I talked initially about meshing of our components. So it is the challenge here is that we are actually adding material gradually throughout the simulation. So we facilitate that by progressively activating the elements. So we actually create elements which are initially empty, and then we have a mechanism that will add material into the empty elements. For providing the thermal part of the simulation, we also have added capability to include moving heat sources. So it could be the welding torch, it could be the laser beam that follows a predetermined path through the mod simulation domain. It also requires some activation of correct boundary conditions, which will change. So we will automatically compute where the free surfaces are. So if you would imagine the thermal aspect of this 3D print, the free surface will there will be some cooling to the ambient. There will be potentially radiation, but convection to the ambient air. And when we add another layer of material, the free surface will be shifted to the current layer. So these are challenging tasks, but we have developed those under the last few release cycles of the code. With that, I'm going to focus a little bit on some of the other products on the SIMULIA brand. One product on SIMULIA is called Isight, and that's really a process management and optimization tool, which you can think of this as being a software robot. So it has a nice drag and drop GUI that will allow us to run different applications, as we can see examples here of Excel, Abaqus analysis. We can do some own scripts, process some of the output from one program, execute, export some results for evaluation or further processing. And once we have that loop, of course, we will allow for creating optimization loops or reliability and robustness studies. And this could be a great tool for helping out on taking decisions. So we can do like trade-off studies and compare multiple different alternatives for product design. And the target with Isight is, of course, that we oftentimes see that currently sort of a classical environment is that we have geometry creation, which have a manual handover to a good team doing structural simulations. At the same time, also fluid simulations, and which is a cumbersome and error-prone process, slow for that matter. But by wrapping Isight around all these different applications, we can streamline and automate the process and speed up the entire simulation loop. Also then including, for example, structural and fluid simulations with combining them into a cost calculation, for example, as we see indicated here. So this would represent like parametric optimization. Another product portfolio that we have is Tosca. So Tosca is then sort of the non-parametric optimization aspect of simulation. It has different capabilities. So topology optimization, as for those of you who are not familiar with that, so that really is capability where we provide a design space where we can have material, and then we have the solver to figure out to remove sort of material with low stresses, and but there are some design constraints on deformations and stresses, for example, so we can come up with the lightest structure that can meet the design criteria. Sizing is a capability to work with shell structures to reduce mass through optimizing the sheet or shell thickness to meet certain design criteria. Shape optimization, this oftentimes comes in association with the topology optimization. So shape optimization allows for minor tuning of surfaces like fillets and so forth to reduce local stresses, usually for the purpose of increase the durability or the fatigue life of the product. Bead is a capability to introduce beads to shift and change the eigenfrequency spectra of our model to be outside of critical range. There's also a similar capability to Tosca structure, but it works on fluid, so we can attach a fluid solver and we come up with optimized geometries for minimizing the pressure drop, for example, and so forth for the fluid flow. Safe is also available on the SIMULIA brand. It is initially an acquisition from Safe Technology in UK. And FE-Safe allows to read results from our structural simulations and potentially multiplying with some loading history and do multi-axial fatigue analysis of the entire finite element domain. So this is in many industries, of course, fatigue can be critical in terms of design. In particular, the more you use topology optimization and that kind of tools, there will be less sort of margin on like fatigue aspects. So it's becoming more important to take that properly into account. So this adds on to our simulation results. It can operate on the Abaqus results databases, and it could write your fatigue life attach them to your strength and simulation results on the same database for visualization. So I will round off this presentation by talking on a little bit about some trends in terms of applications I have noted with the Abaqus usage over the last few years. And clearly one of the things we see is an increased use in topology optimization. So topology optimization can be accessed directly from within Abaqus CAE. So this is an example of the pedal assembly from a car, obviously. And we take the brake pedal here, and we want to explore how we can make this as light as possible, but still meeting the functional requirements. So we isolate that part. So this is taken directly from the preprocessor. So we have some attachment points. You can see that there are some partitions over here, which will be frozen. So these will be we'll have to have these fixed because they represent connections to the rest of the pedal assembly. And the brake pedal itself, where you put the foot, this is where the load comes in as well, will obviously be a frozen region. So the rest indicated by these green glyphs here are sort of the design domain. So these are feasible locations of material. And then we can kick off simulation. And what we see here is an animation of how the topology optimizer, how it finds there are multiple runs, multiple iterations, where we remove material, rerun the simulation, and re-evaluate the simulation with the the constraints in terms of deformations and stresses for this. So this, of course, is a significantly less mass than this initial proposal. I also see a strong trend more recently to take simulation one step further, to also include the manufacturing simulation and the manufacturing history into the picture. And this is particularly important when as we see a new shift to new materials, new manufacturing processes. 3D printing is one example. Composites, for example, oftentimes also are sort of tightly, the effectiveness of the composites are tightly integrated to tie into the manufacturing process, whether it's actually producible at all or if it's easy to produce that. So in that context, we also invoke or develop a number of multi-scale simulation methods. So this offers a capability to extend from the macro scale continuum mechanical level into the microscopic level, so to take into account the constituents of the components. If you have concrete, it's kind of cement and rebars and rocks and so forth, or any type of composite for that matter. So we have offered different techniques to facilitate what we call multi-scale simulations, which is becoming more common that our customers are using. I also mentioned composites, where the manufacturing process is kind of tightly integrated with the ultimate product performance. So there is an add-on capability inside Abaqus CAE to allow for modeling of the manufacturing process of the composite. So we can just see how fiber orientations will evolve as we do the draping. We can change the initial orientation of the plies as we apply them to facilitate the desired properties at the end of the day. It can also explore where we actually can, if we actually can produce it, or if we need to introduce some splits. You can imagine the analogy when you trying to wrap your Christmas presents, whether the paper will wrinkle or not. These are kind of things which we obviously want to avoid when we do the production of composite plies. I also mentioned additive manufacturing again previously. So to include welding in the simulation history of our products. You know, welding is widely known to produce problematic amount of residual stresses because of the thermal history. And the capabilities that we have for additive manufacturing actually lends themselves very well to do high fidelity welding simulation. So we can sort of use that framework to add the material representing to the weld material. And we can add heat also following a predetermined path. And as such, we can make a much more higher fidelity prediction of the product and performance, because this residual stress is oftentimes being the result of the welding simulation. They interact with the fatigue life, for example, or potentially also the distortions. Once this thing cool down, it's anyone who have been trying out welding know that it's fairly common that these products actually distort when they cool down. These kind of things can be captured by including this in the simulation history. All right, so I think this kind of concludes the overview of how we can use what we can do with simulation, and hopefully we all realize that a lot of these things are necessary for us to further improve product performance and becoming more efficient, more economical. So we need both linear and nonlinear behaviors oftentimes in the simulation world. To do real simulations or sort of real product life simulation, we rely heavily on advanced contact and material modeling. Model tends to become large, so high performance solvers, multi-core simulations, execution are required. We can use Abaqus CAE to integrate with CAD packages and also customize and capture repetitive and routine tasks, and also provide advanced workflows for less sophisticated users. So it's really a single solution for all analysis needs. Okay, that was it for me. Thank you for listening. If there are any questions or comments, this would be a good time to.
Yeah, thank you, Jan, for a great presentation. Very exciting software. There are actually a couple of questions here, if you have time for those.
Yeah.
What different CAD models can be imported into Abaqus?
Yeah, we have neutral sort of CAD. Most of the neutral CAD formats are like step IGES, if you will, but it's most of those formats. We have direct interfaces to SolidWorks, CATIA. We have to Pro Engineer. We also have these associative interfaces, which are sort of more intelligent than the kind of the neutral CAD formats.
Okay, good, yeah. So another one here is, can material test data be automatically calibrated?
Yeah, that's another interesting thing, because we for advanced analysis we rely on oftentimes on advanced material models. So for example, it could be even metal plasticity or rubber type material like hyperelasticity, and for hyperelastic and for metal plasticity and so forth, there is a built-in calibration tool that provide the user to feed in test data, which normally would be a tensile test or the equivalence of that, and we can calibrate coefficients or properties for the mathematical models in Abaqus for you. It's not currently sort of fully for all types of materials, but for hyperelastic and plastic materials, we have that.
Good, perfect. Last question here is, can you do a fatigue crack propagation analysis?
Yeah, that's the crack under the failure and fracture and failure portion here. There was an example where we had a crack propagating through the mesh, sort of. Not so. So this is not necessarily, or actually, it goes right through the elements, not in between the elements and so forth. And this is an enhanced element formulation. We can combine that with crack growth parameters like Parry's law, if you will. So if you have those parameters, we can run a procedure we call direct cyclic, which applies a repetitive cyclic loading, and that based on fracture mechanical energy and so forth, it will predict the rate by which the crack propagates. So generally, I would say the answer is yes. It requires some knowledge about the fracture mechanical properties, but yes, we can do that.
Okay, great. Thank you, Jan. So thanks for a great presentation, and I hope you have a nice day.
Yeah, you too.
Mm-hmm.